So in this video clip, we're going to go through a Python notebook implementation of the Dumas Fleming Whaley model, which was published in the Journal of Finance in 1998. And it addressed how to structure best the volatility surface, the implied volatility surface. And what they found was that an adjusted or an ad hoc Black Scholes model performed better than some of the models proposed by Derman Canny, Peer, and Rubinstein in the earlier part of the 1990s, and said they could get a better fit in terms of implied volatility. So a key finding in the literature has been that the volatility, the Black Scholes volatility, implied volatility, is not constant, although that's assumed in the original Black Scholes model, that when you view volatility when you're pricing an option, that the option volatility, the volatility of the underlying asset's return is constant. But in fact, we know it's not constant. It tends to be skewed and also is affected by the maturity of the option. So key findings of the paper were that the Black Scholes constant volatility assumption, the Black Scholes models assumes constant volatility, which often fails to align with real market data, that in fact we get what's known as a volatility smile or skew. There was some empirical analysis in the paper using S&P 500 index option data, which would have been a European option, typically index options based on stock indices are European in nature. The authors found that the implied volatility vary consistently both with the strike price and time to expiration. So it would appear that exercise and the maturity of the option has an effect on the implied volatility. And then testing the deterministic volatility function, the authors tested the deterministic volatility function proposed by Derman Canny, De Peer, Rubinstein, which suggests that the volatility is a deterministic function of an asset's price and time. And comparison then with the ad hoc Black Scholes model, their results indicated, so Dumas Fleming Whaley, their results indicated that deterministic volatility function did not outperform a modified Black Scholes model that allows for implied volatility to vary. This ad hoc model, while less theoretically sophisticated, provided better predictive accuracy and hedging performance than the DVF. Right. Okay. So in the notebook, basically what I'm doing here is I'm following the approach developed by it's a textbook example that I'm using, and the paper, the textbook is from Fabrice Rouah and Gregory Weinberg, and the link here is to option pricing models and volatility, right? So I've taken an example from this textbook. It was an Excel example that used VBA. I've made some modifications to the original spreadsheet, but then I recast it to the Python notebook. So having an understanding of the spreadsheet model actually is fairly important here. But what Rouah and Vainberg demonstrate here is they set up an implementation, a relatively simple implementation of the Dumas Fleming Whaley model in Excel. And that model, I can go into my downloads here and we can take a look at this specific model. So the model, I'll leave a link to the model. But if I try to open here in the downloads, I should make sure I go to properties and then unblock, apply, okay. And then we can go in. So it's not so much in this example, I'm looking or particularly focused on the Excel example. It's more how that can be parallelized in Python. But the basic example that was given here was that Rouah and Vainberg in their textbook took this basic data. They say if you look at any option chain, whether it's, for instance, on Yahoo Finance, or if I go back here for a moment, on Yahoo Finance, or let's bring it in an example. Yeah, so if you take the Nifty 50, currently it's at 24,000. I'm not sure if the market's currently open, right? But just to get a sense of what the option chain looks like, currently the Nifty index is at 24,304. And then you have an array of different strike prices for both calls and puts. And you've bid and ask for each of the options. So basically we're looking at what people are currently bidding and asking for call options where the strike price is 24,450, when the current market level is 24,304. And you can see here we have calls, we have puts, and then when the exercise exceeds the current market level, you get that change in coloring. So we go from out of the money to in the money, or in the money to out of the money options in the setup here, right? And then again, we can move that along to different dates going into the future. So these options expire the 5th of December. Now there's not much activity, but possibly the market is shut. I'm not sure if the market's currently open right now. But you can see that there's a range of different bids and asks that are currently up there, and some activity, and probably we can see the volumes, which vary depending on, on the maturity date and proximity to the current stock index level. You can go out to the 26th of June when those options mature, a little bit less activity, and further out. So on the surface, there would appear to be options that mature. The most liquid options seem to be the shorter term options. And then the longer dated options that have longer maturity dates, where you go out a number of years, perhaps very little activity. Okay, so if we were to replicate that now, the US market's currently shut, right? So, but we can take a look at Yahoo Apple and look at the option chain for Apple. So here is the current stock price. Apple's not trading right now, and the market's not open, and you have a series of options then as well. So if I click here in the options, it brings up in this organization, the page of calls, and then you have puts, right? And you have varying exercise maturity dates. And then you have a sequence of different strike prices or exercise prices on the options. And when the exercise goes from being below to higher than the current stock price for Apple, you can see that there's a change in color here. A lot of the trading will happen where the exercise is relatively close to the current Apple stock price. Okay, so that's just to give you sort of a sense of what the option chain looks like. Now, in the example, the Excel example we were working through here, this is from Weinberg and Fabrice Rouah, right, their textbook. If we know the current stock price and the risk-free rate and the strike price, the bid, ask, and the number of days to maturity, then we can infer what the implied volatility is using this function here. And again, to understand a little bit the workings here, if I go back into our model for a moment, right? I have a number of video clips embedded in this Colab that explain how to work through implied volatility. So one, we're using goal-seek, and the next one using a bisection function, right? So you can take a look at those, and I'll post a link with the video clip. Okay, so if we go back to our spreadsheet here for a moment, I have this function in the developer tab, and we'll bring that in. We'll take a quick look, and you can see when we apply the bisection function, and I'm going to use it for the call here, right? We have the Black Scholes model, and then we take our function, right, our VBA user-defined function, and embed that into the bisection function. So a fuller explanation is in those other video clips, but just so that we can see here in the Excel spreadsheet, I've developed the implied volatility function using the bisection technique. And that means if I know the current stock price, current risk-free rate, strike price, bid and the ask on the option, and the number of days to maturity of the option, and assuming that Q is 0, then I can figure out what the implied volatility is. Okay, so we could use a goal-seek here, but it would be too cumbersome where we have, let's say, 20, 30 options. So it's easier to take the user-defined function and just drag it across the data. And what we typically get then when we observe the graphs here, which are based on the exercise relative to the implied volatility, we get that stylized type shape that we typically see with options, that as we change the exercise price relative to the current stock price, that the implied volatility tends to fall. We might get a skew. Sometimes a smile might be more typical, a symmetric smile, more typical of exchange rate options. And a skew or a smirk is more associated with equity options. And for longer dated options, you get a sort of flattening out. So here it's for the 390 days. 390 days, and you tend to get a flattening out of the implied volatility. So it sort of reverts back to being looking almost constant, but not quite constant. Still a bit of a skew, but not as dramatic as what we have up here, where we're going from 60% down to 20. Here we're merely going from, I think, 25 to just below 20. So it's more some moderation. Now, what Dumas Fleming Whaley propose is that we should model. Instead of maybe applying the deterministic volatility function approach, instead of applying the approach developed by Derman, Canny, Rubinstein, and so on, the pure, we could use a more straightforward, simpler approach, which says you can model the implied volatility based on the exercise squared, the time period squared, and k by t. So essentially here, we run an OLS model. This is model 3 here. We can, if we knew the implied volatility and regressed onto the implied volatility, the exercise squared, the maturity squared in days, in years, and k by t, the product of the exercise and the maturity, we could develop a forecast for the implied volatility. And so the idea would be, if I know the strike price and the maturity and the implied volatility, which I estimated here using the bisection function, we could set up a regression where we take these columns, these variables, and regress onto implied volatility. So if we look at the numbers here, we're taking the strike and the square of the strike, the number of days divided by 365. We square that in turn, and we take the product of k by t, and then take the variables, our x variables, our y variable, and perform a regression. Now that's easily set up in Excel, and I've used the tools here, the built-in tools for estimating. So if I go to data and come across the data analysis, I could set up a regression here in a relatively straightforward fashion. Just come down to regression and set up our data. So I could, just to show you that for a second, if I copy the data that's here and go into a new sheet and go Control V, and if I wanted to run the regression, I go to data analysis under the data tab. Now, if it's not there, you can go to the add-ins and add it in, right? Select here regression. And then our Y variable is, we can include the label. And the independent variables is k squared, t squared, and k by t. Output range we can leave in the same, we can put here in the same worksheet, and be careful to include the labels. If you incorporated them into the mappings, then when we hit OK, we get our regression output. And what's satisfying here is that we can see the R squared, adjusted R squared, 84%, and then the parameter values that we obtained here in the regression represent A0, A1, A2, A3. So if we look at that model tree, then when we go back to the output from the regression, right, we can see this is our A0, A1, A2, A3, A4, A5. Likewise, I could have used the linest function and obtained the same results here using the built-in linest function available in Excel, and I would have got the same values. Notice that the R squares correspond. The R squares 86 and 86. Standard errors, and we can compute the t values by taking the ratio of the coefficient divided by the standard error would produce the t values. All the t values exceed 2 in absolute terms, so all statistically significant. Okay, now for when we do this in Python, right, if I was to take the same approach in Python and set up, right, now the first example here I use C++, but strictly speaking, I don't need to use C++. I'm more interested in Python, but I left that there, and plus an explanation how you would run the bisection function. I'm more keenly interested in setting up the Python artifact that corresponds or parallelizes what we've been doing in Excel. So the basic idea is we have the Black Scholes model. And then, so that looks familiar, accords with the Black Scholes formula that we have here, the Python code, this user defined. Now I need to import my libraries because we need to invoke pandas, numpy, and statistics library, so SciPy. Normally, when you run the first cell, it takes a little bit of time to connect to the server, right? And then we come down. So we're just importing our libraries. And then we want to run our Black Scholes call function, right? Which corresponds to estimating D1, D2, and then the value of the call. I'm just going to look at calls here for the moment. I haven't put in the puts. And then the bisection function. And this code here corresponds to the code we would have seen in our Excel spreadsheet. This bisection function here, right, that VBA, right, corresponds to the Python code we have here, right? Same idea. Now, in terms of what typically is happening, the idea is that the real world distribution of the asset price return, annualized asset price return, the volatility of the annualized asset price return is more fat-tailed. So more extreme events are likely to happen. And for equities, we have that stylized shape where we're looking at implied volatility relative to its moneyness. And for equities, there's more evidence of skewness. And I've left a little discussion here and another Python notebook that looks at the relationship between the S&P 500 and the VIX, which also shows that classic relationship when the S&P 500 drops, the VIX tends to go up. Okay, and volatility surface, an example from Hull, the Hull textbook, could be cast like this, right? That you have different time periods and different moneyness. Okay, now following the approach then set out by Dumas Fleming Whaley, Fabrice Rouah, and Gregory Weinberg in their textbook, right, develop the Dumas Fleming Whaley model, the ad hoc Black Scholes model, where to say, look, you can estimate that model tree, which is what we've done in Excel. And we want to parameterize the coefficients. We want to estimate the coefficients where we take the implied volatility and estimate A0, A1, A2, A3, A4, A5, and then use that in the model, a fitted volatility model, to produce an estimate of implied volatility. So if we take all the options in the option chain, like what we have here, for different maturities, if we put that into a spreadsheet for a given moment in time, then we can estimate A0, A1, A2, A3, A4, A5 using OLS. Should never be negative, so that's why we're saying maximum of this very low value or this. If the model throws off a negative value, we can't use negative volatility. And then if we know the maturity of an option and the exercise of an option, we can predict or we can fit the volatility corresponding to both the exercise and the maturity of the option. Now, because it's for a single moment in time and this is not a time series data set, we can just take K and K squared, but sometimes you see K divided by S as a measure of moneyness, right? But that's where we're going through different, time periods as opposed to a snapshot in time. But for the model that we're using, it's a snapshot in time. Now, what I try to do then is take the values that we would have observed in Excel here. So if I go back to the raw data, I take these values again, and I try to replicate this in Python. Right, so if I go back into the spreadsheet, right, I say, okay, let's set the value of the stock price to 83.53. That's a snap of the spreadsheet, bed it into the text cell here. And we have interest rates 3%, dividend 0. Now, if I run this cell, it won't work because I'm looking for data that I didn't load in. So I need to load in my data. And I have a data file which must go into the content folder. So I need to get the test option data. We'll take a look at what's in there in a second. Right, so I upload. And it takes a second. And then go into the test option data. And just see that come in. Now, does the name correspond here? It does test option data. So this should now run, right? And if I so the data object we create is df. That means the data set that we had in Excel has come in. So the df are all the options that were in the example given by Dumas Fleming Whaley. So this df here, we can create an interactive sheet. It's a new feature in Colab where we mount this in a Google Sheet, although I did upload the data from a CSV file. So just to get a spreadsheet view, we can link it to a spreadsheet in the Google Drive. Okay, now it should open up, but all I'm trying to do here is show what the CSV file looks like in a spreadsheet. So basically, if you look here, we have K, call price, the call bid, the call ask, and the maturity of the option. So those values correspond to what we saw before in the spreadsheet. But that's really basically the CSV file. And that's what df, this data object df, is carrying that data set that was in the original Vainberg and the Fabrice Rouah textbook. Okay, now I want to replicate the steps in Excel. So I want to produce the implied volatility. We already have the call volatility function, user-defined function here that we developed above, right? And I need to create in the df, in the data object, I want to create a new column which is the average between the call, bid, and ask. So that'll be a new column in df. And we want to introduce into the df data frame another column for implied volatility. So if I run df, if I don't execute and I just run df, this is our data object. When I run this cell, it'll create a new column for both the mid price between the bid and the ask, and using bisection function, implied volatility, a column with implied volatility. Let's take a look now what happens. And you can see we have two additional columns. Again, we're replicating this set of numbers that I have here, the 62 to 58. If we check our Excel, 62, 58, the last value is 18. Okay, if I go down, the last value is 18. Okay, now stylized representation of implied volatility often looks something like this, but not guaranteed, right? But typically we're finding that type of pattern in our data, right? That's a snap that I've taken from Dumas Fleming Whaley. And we can create this new df that we've created. I can put it back out here into the content folder. So you see this data set has now been saved out as a CSV file with that title. And then next, I want to run the regression, set up the regression analysis. But initially here, I'm going to, and this is the great advantage of using Python, generate the graph. So it's, I want for each date to generate the implied volatility. And what you observe here, right, is the same as what we had generated here on our spreadsheet initially. In other words, I'm taking the exercise price and comparing and doing a scatter plot with the implied volatility. So that graph is one of four. The final one here for the final maturity for the 390 days is the implied volatility for these different strike prices. So basically, I'm doing the same in Python, but I've just generated 4 graphs for the 4 maturities. And then I'd like to cast that using Plotly as a 3D graph. And Plotly has the advantage of being interactive. So we can create the 3D graph and look at the actual implied volatility. So this is not the fitted implied volatility, it's the actual implied volatilities from the bisection function, right? And then below, I'm going to take model 3. So this is a snip from the Dumas Fleming Whaley paper. I'm going to estimate model 3, so A0, A1, A2, A3, A4. Let's set that up. Right, so we're saying I'm reading in the data from the calculated IV. I'm going to have K, K squared, T, T squared, and K by T. And then set up the independent variables X and the dependent variable as Y. And we can see what X represents. And we can verify what Y represents also. And then using the stats model, which gives us a sort of more traditional type of econometric framing or output, we can estimate using OLS the coefficients on model 3. And what you'll note here is the values we've obtained here in the R squared, the 86%, and the values here correspond to what we saw in Excel. So I just snipped that in and pasted it into the text cell from Excel. So the 12395 corresponds to what was in Excel when we ran our regression. 1239 rounding, and then KT 0.055, T values, right? They all correspond to what's in our Python estimation. Okay, now we would like to map that out. So map out the fitted, right? The fitted OLS model, the model 3, and the shape becomes more quadratic, right? Because essentially, and all the different X and Y's, the time to maturity and the strike prices, they all fill out, right? So it sort of completes. So the red here is the based on our data set, and then the surface is the quadratic type representation of the surface. Okay, so now the implied volatility and those values, we can try different versions of Plotly. I don't think I've improved it too much. Just to put some kind of grid in there, doesn't make much difference. And as we go through here, we could consider perhaps other types of estimation techniques. So probably need to put in a text cell here, introduce machine learning. Where machine learning, we compare the goodness of fit and accuracy of OLS relative to random forest, which is a machine learning model, random forest, which tends to bump up, quite good at picking out non-linearities in data. So in terms of setting out a strategy then, or espousing some strategy, if we took the Dumas Fleming Whaley model and went beyond, so in the original paper, Dumas Fleming Whaley, what they introduced was you estimate an OLS model where you parameterize A0, A1, A2, A3, A4, A5. What if we were to take the exercise squared t squared k by t, and use a random forest model, which would be trying to harness some of the power of machine learning to pick out, to deal with the nonlinearity here. It's a bit of a black box. If we were to apply that type of set of techniques, could we bump up the accuracy, which was 86% for the full data set? So in that instance, just applying standard libraries from sklearn, so linear regression and random forest, right? And I do the features k, t, k squared, t squared, k by t, same x and y as before, and do a linear regression type model. But importantly here, we want to assess the accuracy of the model in terms of its mean squared error and R squared, right? And take a look at the accuracy of the model. So for the full data set, OLS is producing an R squared of 86% and random forest 99. So that's a little bit flattering, right? And you can see how the fit is very good. And then if I do a test train split on the data, which means we hold 20% of the data back, or maybe 30% of the data back here, 30% of the data is held back as a test, and we train the model with 70% of the data and apply the same analysis, but then try to predict with the holdout data. So we use the train data to estimate the model, and the test data, sort of the outer sample data, to test how good the model performs when we go out of our data set. We see that for linear regression, the R squared is 56%. With the test, we use the test data. And for the test data, OLS drops down quite considerably to 56%. But for random forest, the R squared is 73%. So you can see when we take the actual implied volatility and compare against predicted from OLS, we've quite a bit of error, and it looks as if there's a pattern in that. Whereas with random forest, those linearities are captured a bit better. This one looks a little bit to be an outlier, so not so good. But overall, for the test data, right, we're using the test data. For the test data, the accuracy level is quite significantly better with random forest relative to OLS, the original technique proposed by Dumas, Fleming and Whaley. And then if we want to take specific, if I knew K and I knew T, I could predict what the implied volatility is using linear regression or random forest. And random forest is predicting a slightly different level of implied volatility relative to OLS. But random forest is a little bit better, right? Random forest overall is a little bit better. Okay, so that's basically the idea. And it's essentially what we're doing here is we're setting up a surface based on option chain. Initially, the surface is just simply a recasting of the implied volatility itself from the bisection technique. Then we set up Dumas Fleming Whaley, the ad hoc Black Scholes model, and we generate the surface. Why am I focusing on the surface? Well, you tend to see quite a bit in, if we go to Bloomberg and we just get an image of the volatility surface. Typically, when it comes to option data, you're very often trying to model the data something like this, right? Your option, now that's not a stylized representation, we'd have some skew, but you can get different shapes on your data, right? More typically, you're getting, for the lower exercise prices, the implied volatility is a bit higher than for the higher exercise prices. And then you have maturity, a flattening out over time as the maturity increases. There's a flattening out of the implied volatility. Again, different patterns emerge, right, on your data. Okay, so we set up the model to try and frame a little bit how do we generate an implied volatility surface. In the spreadsheet example that I used here, to estimate the surface, I parameterized the OLS model, and then for the surface, right, I used a data table. So I took the values of k squared, t squared, and then so if you like, I estimated what the implied volatility was and set that up then in terms of k and t. And that allowed me then to generate a surface with the data supplied by Fabrice Rouah and Gregory Vainberg. Okay, so we've taken the Excel model, the simpler, more primitive type, the Excel is very intuitive, and we've tried to add on some interactivity in terms of generating the surface. And then finally in our Colab here, we've set out an implied volatility surface, an implied volatility estimation, where we introduce some machine learning in the form of random forest. And we get a little bit of a bump up in the accuracy of the model in terms of its mean squared error and R squared. And we also apply that idea of a test train split. Okay, let's leave that there. The files and so on, I'll supply in links to the in links to the video clip. So let's bring that up.